We're going to continue our exploration of chapter 23. The thing you have to remember about amines is, the most important thing, is that they are bases. Bases react with acids. And here we're going to put our bases in order of increasing basicity, with the weakest base first. There's a section in the textbook that talks in depth about this, and I'm assuming everybody's read it. Our first two amines, here are the amines, and I will also draw their conjugate bases. And conjugate bases in green, or sorry, conjugate acid in green. These are the bases. Okay. Butylamine in blue. What does butylamine become after it picks up a proton? Butylammonium ion. pKa is roughly 10. That's one we learned a long time ago. Diethylamine. 2 ethyls on a nitrogen. Conjugate acid. Diethylammonium ion. Imidazole. Yes, you must learn how to draw imidazole. That's a good start right there. There you go, imidazole. Now, as discussed several times in the book, and, oops, let's do it in green, shall we? And in many videos, imidazole is the most important biochemical base. It is one of the residues in proteins called histidine. And histidine picks up a proton here. Why there and not in the other position? Because this can still resonate with the lone pair on the other nitrogen. And even more importantly, this is still aromatic. If you put the proton on the wrong nitrogen, it is not aromatic anymore, and it does not have resonance stabilization with the other nitrogen. Okay? So you got to put it on the sp2 nitrogen. There you go. And it's a pretty good base because of the stabilization of this. It's not quite as good a base as either of these two. We'll talk about that later. 2-methylimidazole. Oh, that's a copy-paste job if I ever saw one. And 2-nitroimidazole. We got methyl versus nitro. Methyl, methyl, nitro, nitro. 2 positions. Pyridine. Looks like benzene, except one of the corners is a nitrogen. We learned that a long time ago, I hope. Only one nitrogen to choose from here. No tough choice. There we go. Pyridinium. We've seen the name pyridinium a couple times. We saw it in PCC. It's the cation. It's the P of PCC. 4-methoxypyridine. Copy-paste job if I ever saw one. 4-methoxy. 1, 2, 3, 4. OCH3. OCH3. Yes, this lone pair can actually resonate with the plus charge on the nitrogen. It's really helpful. So that's going to be a more stable acid. Therefore, the base was a better base. We'll talk about all that when we get there. Aniline is aminobenzene. We have to know that. The aniline ion is hard to make. We'll talk about it in our part B. There. So we got everything there. These are the guys we're talking about. So the best base here is the dimethylamine. Diethylamine, sorry. Okay, why? Well, it's a cation when we form its conjugate acid that is stabilized by two things. That is the best base because this conjugate acid has the best combination of hyperconjugation. It has two carbon groups, so that stabilizes the plus charge, and hydrogen bonding with the solvent. And if you remember, a pKa reaction is the reaction with water. The reaction of an acid with water is the pKa reaction. We can't forget that. So there is water present during the experiment where they come up with pKa. So if you can hydrogen bond with water, that means it's going to be easier to make the conjugate acid. It's got two H's for hydrogen bonding. It's got two carbons for hyperconjugation. That doesn't depend on water at all. Whereas the one to the left of it has lower hyperconjugation. It has better hydrogen bonding, but apparently the hyperconjugation is too detrimental compared to the hydrogen bond. So this one is second best for the reasons given in red. So the best is 2. The second best is 1. So we're looking at our normal amines that we studied in way back in 241. And yes, those were good bases. pKb was around 4. That's 14 minus 10. That's a pretty low number, 4. And that didn't change. There's nothing new here, really, except for this discussion about hyperconjugation versus hydrogen bonding. And if you look in the textbook, there's a very nice, the page is in order already. That page is designed for your test, okay? It's got these alkylamines at the top of the page, and lower down it's got the imidazoles because they're number 2. You have a nitrogen that's sp2 with a plus charge. That's never going to be as good as a nitrogen that's sp3 with a plus charge, because sp2 brings everything closer to the nucleus, 33% S. If you're bringing a plus charge close to the nucleus, this is not good news. Think about it. What's in the nucleus? Protons. You're bringing plus closer to that? No, thank you. Not as good as these two, where the plus is on an sp3 nitrogen. So you need to say something about that. Why are these second tier, these imidazoles? We'll go with baby blue. And I'm going to be liking this one the best of these 3. I got to state that sp2 N plus 33% S is not as stable as sp3 N plus, which is over here. So that brings them below the red category right there. And then I like, these do have resonance stabilization. All three, that's 3, 4, and 5. N pluses are resonance stabilized. That's a good thing. And then I just have to talk about the methyl group versus the nitro. CH3 stabilizes N plus via, or via, depending on how you want to say, hyperconjugation. And I'm just going to go over here and say, well, right down here and say NO2 destabilizes N plus via inductive effect. The inductive effect is usually a good thing, but hey, if you're trying to pull electrons away, which is what the inductive effect does, you're trying to pull electrons away because you're very electronegative, and you're trying to pull electrons away from something that's already positive, no thank you, not as good. Plus positive means you're missing electrons. And now you're trying to pull electrons away from me? No. So of those three, the nitro is the worst, the methyl is the best, and in the middle is the Roman numeral 3. So we'll put those all in baby blue. Roman numeral 3 in the middle. The methyl is 4, pretty sure, a little better. The nitro is the worst, and I'm pretty sure that's 5. And I'm pretty sure we have to move this now. If it lets us. It won't let us. You're so mean. Yeah. That 5 is gone. I'm sighing. There we go. Technical issues. At least it slows me down, right? Okay. So second tier is always the imidazoles. First tier is always the aliphatic. Some of you have never seen that before. These are aliphatic. That is just a old school way of saying they're saturated like a fat, F-A-T. Saturated fats, you've heard of those, right? There you go. They have no double bonds. Okay. I will not get into the context of PHAT versus FAT. That's old school, right? Okay, good. Next tier of bases is pyridine. Kind of have these in order already for you. I wouldn't count on that again, but they are. The pyridines are the next family down. And the reason is they got the sp2 reason again. N plus on an sp2 is nowhere near as good as N plus on an sp3 carbon. Or sorry, the N plus itself is sp2. Talk about attached to. Let's talk about your existence. You're an sp2 N plus, and you don't have the resonance advantage of these two. So you don't have this little comment going on with here. And I know you're arguing with me right now. You're saying, well, they both resonate with aromaticity. Yeah, you're right. But that's a constant between all 5 of these. They're all aromatic. Okay? Every one of them is aromatic. So let's not compare one's aromatic, one's not, when they're all aromatic. That's not a comparison. The N plus here can resonate with the other nitrogen, and there's no other nitrogen help on these. Although the oxygen help is going to help this guy a little bit. We'll talk about that in a second. So I guess we'll go with hot pink. This comment, still relative, same. No resonance with another nitrogen. So compared to the previous category, that's why these aren't as good. And we're going to say OCH3 stabilizes N plus, not via hyperconjugation, something even more powerful. What's that? That's what I want to hear. Resonance. Okay. So pink is going to put the better one that has the OHCH3, which is VII. And not quite as good as the one without the OCH3. And that's a less than sign there. It just looks terrible. VII less than VI less than. And then we're going to just talk about aniline. We'll put it in purple. It's the worst. Anilines are always the worst. There's our final answer. We'll highlight it. Good old yellow highlighter, old school. I don't even know if you can see that on the screen in this room. I know my old room, that used to just not even show up at all. That's there. And we got to talk about why aniline is a lousy choice of base any day of the week. And it starts up there. This lone pair can resonate with benzene. And now you've taken away that lone pair. Lone pair gone. Resonance gone. Well, the resonance for the benzene. That's a terrible situation. Aniline was very happy all by itself, resonating away. And then you put a proton on it and say, you took my resonance. I want it back. Put this proton somewhere else. I can resonate again. Thank you. And that is the end of that. There's your big picture. That's the end of our story.